All right, here's the second video covering section 2.5 in your book. We're still in the subsection involving limits. And in 2.5, we talk about limits involving infinity. But unlike the last video, where we talked about questions where the answer was infinity, and that's informally speaking, we saw some where it was positive infinity, some where it was negative infinity. In this section, the question is going to involve infinity. And what do I mean by the question involves infinity? Well, before I get into an actual example from this section, what I want to do is follow a format kind of similar to what I did in the last video, where I remind you of something you knew how to do, and then kind of show you a slight tweak on that something, and the slight tweak will be the material from this section. In the last video, the question that I wanted to remind you of was a question from Calculus 1, a relatively recent math class that you took. Not the case in this video. In this video, I want to take you all the way back to pre-calculus, Math 111 at our school, where you were asked to describe the end behavior, that rings a bell, of some rational functions. And the way you describe the end behavior was typically with mathematical sentences, either describing asymptotes or something that looks something like this, with something in place here and something in place here, essentially telling the reader what happens to the y value when the x value gets really, really large, think way off to the right side of your graph, or when the x value gets really, really large negative, think way off to the left side of your graph. Or in the case when you had a horizontal asymptote, you might describe the end behavior by just telling the reader where that horizontal asymptote was, maybe a sentence that looks something like this. So your answers would take on one of two forms, one of these two boxes that you see here, and we would just have to evaluate the rational function to figure out which of these two forms our answer would take on and what goes in place of the blanks, what goes here and here, or what goes here. And to fill in the blanks, all you really had to do was look at the degrees of the polynomials that make up the rational function. So as a reminder, the degree is the largest exponent you see, so this polynomial has degree 2, and this polynomial has degree 5. And anytime the degree of the denominator was bigger than the degree of the numerator, you filled in the blanks with zeros. So you could say that when x gets really, really large, the y value approaches 0. And when x gets really, really large negative, the y value approaches 0. Alternatively, you could just say that the graph has a horizontal asymptote at y equals 0. And informally, the logic here was you only have to look at the degree, because when x is really, really large, whether negative or positive, this term kind of dominates this term. Negative 3 times a million squared is so much bigger than 6 times a million that you can essentially ignore 6 times a million, and also you can ignore this 9 right here. So that allows you to just look at the degree of the polynomials, or more specifically the terms with the largest degree. And then when the denominator has a larger degree than the numerator, this term gets so much bigger in terms of absolute value than this term that the entire quotient tends towards 0. An idea we'll make a little bit more clear when we talk about the Math 252 example. The point was just you could memorize when the degree of the bottom was bigger than the degree of the top, you put in zeros there. What if it wasn't? What if the degree of the top and the bottom were the exact same? Well, then you could write sentences that look a lot like these, except now instead of putting in a 0 in all of the blank spots, you put in the quotient of the leading coefficients. In other words, you recognize that x to the fourth is the term with the highest degree in the numerator. Typically it's written first, but it doesn't have to be. And negative 4x to the fourth is the term with the highest degree in the denominator. And so you ignore everything except for those two terms, and then you cancel out the x to the fourths, which we kind of sort of justified in Math 111, but not really, but you let it slide. And then 2 divided by negative 4 is the same as negative 1/2. And that negative 1/2 is what would fill in all of the blanks here. I could say when x goes to infinity, y goes to negative 1/2. When x goes to negative infinity, y goes to negative 1/2. Alternatively, I could just say the graph has a horizontal asymptote at y equals negative 1/2, and that would be describing the end behavior. And so this was the case when the degree of the denominator was bigger than the degree of the numerator. This was the case when the degrees are the same. There was this third case when the degree of the numerator was larger than the degree of the denominator, in which case you don't have a horizontal asymptote, so there's only one way you can write the end behavior. And it looked like this. And now to fill in the blanks, you could still ignore all of the terms except for the ones with the highest degree. So in the numerator, you ignore this plus 1 and just look at negative 3x to the fifth. In the denominator, you ignore this x and look at just 2x squared. But then you'd have to do a little bit of work if you're really trying to write mathematical sentences. You might say something like, when the x value gets really, really large, either positive or negative infinity, this function h of x acts like y equals negative 3x to the fifth divided by 2x squared, right? Because the 1 and the x we could ignore when the x values are getting really, really large. And we can divide these polynomials and just call it -3/2 x to the third power. -3 divided by 2 gives me the -3/2. X to the fifth over x squared is x cubed. And then if you think about what -3/2 x cubed looks like, well, the x cubed function kind of sort of looks like this. But if it's negative, I have to reflect it vertically. So I end up with something that kind of sort of looks like this. Right? And I can describe the end behavior of this thing in red. And since my function h of x acts like this thing that's pictured in red, I can fill in the blanks here by saying when I go way to the right on the graph, when x approaches infinity, it looks like this thing goes down. The way I write goes down is y approaches -infinity. When I go way to the left on the graph, this thing in red goes up. The way I write goes up in terms of these symbols is y approaches +infinity. So I had these three different cases in Math 111, probably spent a good week talking about these three different cases, the end behavior for rational functions. This ends up being exactly what you need for Math 252. These same three cases. It's the same analysis. You're going to be asked the same questions. All that is different is you're going to answer them. You're going to give the same answers. You're just going to write it up with a little bit more mathematical notation. You're going to think a little bit more deeply about why these answers are what they are. It won't be because you memorize when the top degree is smaller than the bottom degree, you just put in zeros. It'll have more to do with limits and understanding limits. That's what we're going to be doing in this section. But really, it's no harder than what you did in Math 111. It's the exact same as what you did in Math 111. And to prove that fact to you, I'm going to answer these same three questions. And I'm going to get the same three answers. They're just going to look slightly different because they'll be written in a Math 252 context instead of a Math 111 context. Here's the way the question looks in Math 252. What is the limit as x approaches infinity? Note it could be +infinity or -infinity. If the question is +infinity, the answer is 0. If the question is -infinity, well, the answer is also 0. Right? You're going to be asked some sort of limit. The limit as x approaches. So instead of as x approaches, the limit as x approaches. Same thing. And then instead of listing the rational function separate, we're just going to write that as an expression. This is the limit that we're evaluating. And the way you're going to do this, instead of just memorizing that because the degree of the bottom is bigger than the degree of the top, the answer is going to be 0, which, by the way, the answer is going to be 0. What you're going to do is use limit laws. I can say that this limit is equal to this limit. How in the world did I get from here to here? All I did is I divided everything by x to the fifth power. I divided this, and this, all by x to the fifth power. -3x squared divided by x to the fifth is -3 over x cubed. Right? You can kind of picture an x squared divided by an x to the fifth, leaving you with x cubed down in the denominator. I do that to each of the different terms. The reason I'm allowed to do that is what I refer to as the limit laws, which you were supposed to have studied in Math 251, but I don't want to even get that deep into them. Most students can just kind of follow, oh, right, if I divide everything by x to the fifth, I get from this line to this line. Why x to the fifth? Because that's the largest degree I see anywhere in this quotient, this x to the fifth right here. That gets me here. And now I got to evaluate these limits. Well, we haven't done a whole lot of evaluating limits as x approaches infinity. But really, there's only one fact you need to know for that. It's kind of the analog of this fact. It's another refresher on fractions. And what's going on here is if I take some non-zero constant, like 6, for example, and divide it by a really, really, really large number, the answer I'm going to get is a really, really, really small number, a number really close to 0. Right? We can do the same stupid, I know you're not going to like this, cookie example, where now you got 6 cookies and you have a really large number of friends. You got 1 million friends. Like, good for you. You got 6 cookies and you're trying to divide your 6 cookies amongst your 1 million friends. How many cookies is each friend going to get? Well, damn near 0, right? A tiny, tiny, tiny little crumb. Because you got too many friends. 6 divided by a really, really large number is a really, really small number. If you want to write it a little bit more intelligently, you might say that the limit as x approaches infinity of c divided by x is equal to 0, where c represents a constant. And it turns out in this case that constant can be negative, positive, even 0, and it'll work. If your value of x gets really, really large, then this fraction gets really, really small. We can denote that with this mathematical statement. And it turns out that it's also true if your value of x gets really, really large, negative. For the same logic, right? Any constant divided by a really large negative number is also going to give you 0. It's a little bit harder to do the cookie example, but maybe you could pull out a calculator and take some constant like, I don't know, 5, and divide it by a really, really large negative number, negative, I don't know, 10,000 or whatever that is. You get a number really, really close to zero. That fact ends up being all that you need to answer all of these questions because each of these individual fractions look a lot like one of these guys. We can evaluate this limit by evaluating each of these terms individually. And if you really like to show your work, I suppose you could say that this equals the limit of this thing plus the limit of this thing plus the limit of this thing divided by the limit of this thing minus the limit of this thing. And you're allowed to do that again because of the limit laws, but most people don't. Most people just look at this and they're like, okay, this thing right here, what's this evaluate to? I have a constant divided by something getting really, really, really large. Oh, that looks a lot like this. That's equal to 0. So this term right here is just 0. Similarly, this term is 0. Similarly, this term is 0. Similarly, this term is 0. What I end up with is a whole bunch of zeros divided by 2. What's 0 divided by 2? You're like, oh, I don't like dividing by 0. Right, you're not dividing by 0. You're taking 0 and you're dividing it by 2. 0 divided by 2, that's easy. That's just 0. That's not getting anything weird. It's perfectly okay to do 0 divided by something. What's weird is when you do something divided by 0. This limit is just equal to 0. Oh, right, I knew that. That's that 0 right there. That's the same answer. You're just getting to that same answer a different way. You're not just memorizing that the degree of the denominator is bigger than the degree of the numerator. You're evaluating limits. And you can evaluate limits if you do two things. You divide each of your terms by the largest degree that you see in that rational function. And then you apply these two facts, which hopefully are intuitively true, and you can just look at those and understand them. And that will solve all of these problems. You're like, no way, that just solves A. I bet B is going to be super different. No, it's not. Right? Let's say you were trying to figure out, maybe we'll switch it up a little bit. Say you were asked the limit as x approaches negative infinity of this huge mess. How would you deal with it? Well, if I didn't know any better, I might just follow the same strategy I did the last time. I might look for the largest degree, x to the fourth, and divide each of my terms by x to the fourth. If I did that, what I would be trying to figure out is what is the limit as x approaches negative infinity this time of, well, let's see, divide this by x to the fourth, you just get 2. Divide this by x to the fourth, you get negative 6 over x. Continue doing that for all of your terms, and you get here. Evaluate each of these terms individually. Well, 2 is just 2. There's no x's to evaluate there, but negative 6 over x, the limit as x approaches negative infinity of that, that's just this case right here. A constant divided by x, the x is approaching negative infinity. That just turns into 0. This term is just going to turn into 0. I got 2 minus 0, plus 0, minus 0, plus 0, negative 4, plus 0. At this point, you're probably wondering, do I really even have to write this all out? I don't know. I don't really care, frankly. If you want to go straight from here and just say that this is equal to negative 1/2, we're good. Right? You might want to show this is an intermediate step, but I think after doing one or two of these, everyone in the class will be able to go from here down to here. In fact, I know that you're able to go from here down to here because you were able to go from here down to here way back when you were in Math 111, and you gave me this answer. Right? We're not doing anything new. We're just writing it up differently. So yeah, I guess show your work a little bit until you're sure that you're confident that you could show your work. Then you don't need to show your work anymore. Do one more, part C here, and call this video good. Let's do something that's a lot like this problem. We'll switch back to the limit as x approaches infinity, but you'll want to be able to do this for positive or negative infinity. You'll get lots of practice of that in the homework. And evaluate this expression. Well, I guess if we were trying to use the exact same strategies we used in part A and part B, what we would do is divide each of our terms by x to the fifth, and that would leave us with this. So now we go and we try to evaluate this the same way we've been evaluating things. We got negative 3 plus 0 divided by 0 plus 0, and we end up with negative 3 over 0. Uh-oh, that's confusing. I don't like dividing by 0. What am I possibly going to do here? Well, the good news is that previously you watched an entire video describing what to do when you end up dividing by 0, informally speaking. You learned what happens when you take a non-zero constant and you divide it by a number that is approaching 0. Right? We learned that we got to be really careful with the sign. We end up getting a really, really large positive number. Our answer is always either infinity or negative infinity. We just have to be careful whether it's positive infinity or negative infinity. So this third example here is actually an example that involves both this video and the previous video. -3 divided by 0, well, all I have to do is be really careful and think about this 0 that's down on the bottom. Is it negative or positive? All I got to do, I know my answer is either going to be infinity or negative infinity. I mean, if you want, you can just write that in right now. You can write in infinity and leave a little bit of room where you may or may not put a negative sign. This problem just comes down to whether this thing is negative or positive. How can I figure it out? Well, look at this original expression. The sign of both the numerator and the denominator will be determined by the term that has the largest degree. Informally speaking, it's going to overpower all of the other terms when the x value gets infinitely large, whether it's infinitely large, positive, or negative. So all I got to do is look at this guy and look at this guy right here. Right? X to the fifth, when x is a really, really large positive number, a positive number to the fifth power is a positive number. Multiply that positive number times -3, and you end up with a negative number. So my numerator is going to end up being a negative number. What about my denominator? Well, again, the term with the largest degree is going to dominate the term with the smaller degree, so I can completely ignore this x and just look at 2x squared. A really, really large positive number squared is going to be a really, really large positive number. A really, really large positive number times 2 is going to remain a really, really large positive number. I'm going to have a negative number divided by a positive number. My final answer here will be negative infinity. Oh, right, I knew the answer would be negative infinity because really all I'm trying to solve is what I wrote right there. As a test to see if this made sense for you, you want to be able to go through this same logic here that I did in part C, the limit when x approaches negative infinity. And hint, the answer should end up being positive infinity. If we change these infinities into negatives, your answer should be positive infinity. But make sure you can work through the logic of that. Make sure you can follow how that works out. I think what you'll end up getting is a positive divided by a positive when you go through this same analysis. Those are the examples. If you can do those examples, I think you'll be able to do everything from this section.